Let's get this started then. So this talk is about startup challenges, which in my mind means how do we make the JDK snappy enough for everyone to be happy without throwing out all other concerns which may or may not be more important for us. Both true and false. So at a glance, startup challenges. For startup, there's always been an intrinsic trade-off between startup and other concerns. Most importantly, peak performance and latency. Also footprint, static and dynamic footprint have been primary concerns for many. Startup often has drawn the shortest straw when it comes to the JVM and JDK implementation. Over the years, we've seen startup suffer from the ordeal of death by 1,000 cuts. There's been many features going into the JDK. Many of them, or all of them, have been well-meaning, but oftentimes each new little feature or little addition adds straw to the back of the cart. And now we're faced more and more with the prospect of new language features being more meta, as John Rose puts it. More dynamic setup, more code generation happening to support anything from Lambdas to indified string concatenation. And well, in the future, we'll see even more of that. So if those other concerns are more important, why do we bother with startup? Well, the most enticing opportunity is that by reducing startup of Java applications, JVMs, etc. in general, we broaden the range of applications for which the JVM is a suitable target. That anything from the CLI tools to function as a service to small cloud microservices. It also gives us the opportunity to consolidate efforts targeting embedded solutions and embedded systems. From Java 9 and forward, there is no longer an embedded JDK distributed by Oracle, for example. We are moving to the modular JDK where you provide, using JLink and other means, you can customize your runtime images to be small and contained. You can cut off all the extra luggage. Well, then of course there's the long-standing fight against the misconception that Java is slow. And of course, for everyone working with Java, having Java boot up faster is a quality of life concern. So even though I might be motivated by the things on the top of this list, I might be more personally motivated by the improved quality of life for myself. Anyhow, over the years, a lot of startup techniques has been put forward on the table and implemented. We have CDS, which stems from the days of applets in the browser to make the client VM faster. Since a number of Oracle JDK releases, CDS has been available also for the server VMs and all the parallel and G1 collectors and so forth. CDS has, since Java 10, it also has the app CDS aspect now in open source, so we can not only do the bootstrap of CDS no longer only covers bootstrap of classes from the platform itself, but you can customize it to include application classes, etc. We also, since Java 9, have hotspot AUT, which allows you to generate C1 level code ahead of time. It's based on Graal technology, but I'm not going to go into the depth on this in this talk. There's also JLink, another tool added in Java 9 to allow you to customize your runtime images, to cut away modules that you don't want to see in your image, etc. Also enables various link time optimizations. For example, we wouldn't have gotten close to the startup performance that we have in Java 9 if we wouldn't be running J-Link plugins to optimize away a lot of things, doing verification of the module graphs, etc., that we are doing at link time now rather than runtime. There's also the up-and-coming native image tool from the lab's effort to produce native tools, etc. This is just something I will mention in this talk. I'm not going in any depth of that because that's not anything I've been working on. Anyhow, CDS is very much, to start from the beginning, we have this, we're going to talk about Hello World for a little bit, so please bear with me. Hello World has been as old as Java itself and older still, and oftentimes we see developers run Hello World and measure the time of it and go up in arms about how many milliseconds it takes for Java to run this silly little program. And for now, we'll ignore that running a program from start to finish includes more than startup time and just go with it. So I mentioned regressions in Java 9 mainly due to the module system. We've been here before and talked about this at Lambdas, but not only the module system put some weight on the table, we also had small regressions due to making G1 the default, other runtime features like segmenting the code cache and adding JVM CI. These caused small regressions to the time it takes for the runtime to generate exception stack traces, etc. And turns out we're throwing a few exceptions during bootstrap, and that caused various regressions. The funniest startup regression in 9 was the 14 million or so instructions that were spent calculating VM flag constraints, even if you didn't send any VM flags. But at the other end of the spectrum, we did a lot of startup optimization in 9 to soften the blow. So on this, my workstation, which is quite a slow machine for startup applications in general, I only saw about a 20 millisecond regression, or about 20%. So all the numbers I will show here on these slides is with CDS enabled. I consider that the default run mode for going forward. CDS might be even easier for people to use and will be enabled by default, but that's a future improvement. We decided that, well, this won't stand. We need to optimize away the overheads that were added in over time. So an effort were done during the Java 10 timeframe to well, both optimize away a few of the inefficiencies that was brought in by the module system. Lots of small library and runtime optimization happened as well. The VM flag constraint checks were greatly improved. G1 had startup footprint improvements. CDS was refined even further to pre-resolve string constants, etc. So they load a little bit faster and might come with hash codes pre-calculated and such. And then, well, we kept going. Java 11, that is due anytime soon. We see startup improvements from, well, cutting down the size of the JDK itself by removing Java EE and also the Java FX modules. So the Java FX modules aren't there in the OpenJDK, but they, so anyhow. And library optimizations continued. I mean, there's been I would say hundreds, but maybe that's overstating the fact. But small improvements in every area in the bootstrap sequence, from character data to locales, etc. So all in all, the startup on my machine is now better than it was in Java 8, even with the module system already, even with a lot of new improvements, all the features that has been added over quite a few years. And we are continuing this journey, a little bit at least, to keep making Bootstrap of Java itself faster. So the JDK, the CDS feature of OpenJDK has been improved. Now we are, Zhang Li and Joy has done great improvements to allow serialization of immutable Java heap structures, which we're using to reconstitute large parts of the module graph on Bootstrap. There's also the possibility that in Java 12 or forward we'll be dialing up the encapsulation rules of modules to be a little bit more strict, and as it turns out, that actually helps startup. So that's about it for Hello World, except that, well, why is the Bootstrap cost so much higher in 9? Well, the main feat of this is that we moved quite a bit of initialization for modules, etc., but also some runtime concerns from the native runtime to Java layer. This is an architectural decision that has many implications for the maintainability of the platform, but it did cause a ninefold increase in the number of raw bytecodes that the platform executes to Bootstrap. So at the same time, the module architectural change meant that JIT threads can start a little bit sooner. It was more compartmentalized when concerns could be, when the system could be considered booted up far enough so that various subsystems can boot up and start running. So we also see that JIT activity happens a little bit sooner now in 9 and forward, which means that we quickly shift from interpreted code to JITted code very, very early in the startup. So we can see that after JIT, the orange line in this graph, the number of activity still in the interpreter isn't, too far off the mark. But well, all isn't green. The form factor will what's it called? Your mileage may vary with the type of hardware you run on. My workstation, for example, has many threads, so it throws a lot of JIT threads on startup, meaning that code quickly gets through the hoops of JIT compilation. On a fast but not so many, or with only two cores laptop, we might struggle still to get to the same startup performance as Java 8. That this is due to the lack of C1 threads. Maybe AUT can help you a little bit more on that form factor. But our main concern might not be Hello World, really, even though it's an interesting baseline to keep pushing down. The greater challenges has been how do we go from a freshly booted VM to running more of the high-level features, and Lambda is, of course, one of the more prominent examples. So let's look into the startup of going from an Hello World to a Hello Lambda, and without further ado, the reality of it was that in Java 8, the overhead of bootstrapping a Lambda was actually quite large. And all these numbers on my workstation for booting a Lambda on Java 8 showed a 90 millisecond bootstrap overhead to run and execute a single Lambda. So, well, during the Java 9 development, we started seeing a lot of similar startup regressions happening all over the place, and of course no one was happy with a 90 millisecond startup regression on a benchmark that had been, pretty happy, floating at about half that for quite some time. So we set out an effort to optimize this, and with the goal of making sure that you could use Lambdas during Bootstrap without anyone really noticing. we didn't get that far. The bootstrap costs, well, they were greatly improved. We made the implementation lazier, we micro-optimized a lot. We implemented a JLink plugin to generate lots of the dynamically generated classes needed by typical use of Java Lang invoke to be possible to generate them ahead of time at link time. So quite a few of the shapes, lambda forms, etc., that you generate to set up something like a lambda expression are actually invariant with the use case. They are, boxes and shapes that are quite interestingly trivial in of themselves. But generating them then thus ahead of time gives you some startup benefits. You just don't really know which forms will be needed by a typical program, so you have some profile-guided optimization. So we rebuilt as well the build system to be able to get this 50% reduction. Still it was pretty high, so we kept an eye open to see if we could get rid of the remaining, 40, 50 milliseconds. Not much progress for Java 10. A little bit, a few extra forms were realized that we could generate ahead of time, but the engineering time was spent mostly on other things during this time frame. So for Java 11, by chance, that's why I was looking into other things, we found a way to cut away the remaining overheads by 75%. This came from special casing Lambda bootstrap method to be invoked exactly. What that means is, prior to the optimization we did for Java 11, the static information or static type information that was sent to the bootstrap method were lost a little bit on the way. And that means that when invoking using method handles, you create dynamically, you bind a lot of method handles that whose main purpose is to check the types, do class casts to check that the types of the parameters are what they are supposed to be. And since those are actually statically known for the Lambda bootstrap, that was entirely unnecessary. So a little bit of a gotcha in the implementation. This got rid of the bulk of the startup overhead of Lambdas. We're now down to maybe a few milliseconds, 6 or 7 or so, mainly due to the extra class loading, etc. we still have to do to bootstrap the thing. The question then begs to be asked, can we use Lambdas everywhere now with the overhead so small, or the startup overhead so small? Well, depends. If we scale up the number of Lambdas we execute in an application, basically simulating a more complex application form factor, we can investigate if there's a scaling cost to Lambdas compared to, for example, an anonymous in the class equivalent. And well, if we step through the hoops of testing a class with an increasing number of such Lambdas, we see that the initialization overhead of each Lambda stabilize somewhere around 0.19 millisecond per Lambda on my machine. So there's and on the equivalent test using in the classes, we stabilize around 0.14 millisecond per class. So, well, class loading is expensive, and of course Lambda loading does class loading and a little bit more. So there's an overhead there that we would like to, of course, deal with. But over a large equivalent application, the overhead is now quite manageable. It's like 100 milliseconds or so, even after scaling up to 2,000 Lambdas. For most applications, that's perfectly fine, but well, we still want to do better. To do better, we have to dive into Lambda translation. Others before me has given better rundowns on how we how we translate Lambdas, but let's look at it quickly. So Lambdas are basically translated by Javac into private methods. For example, this example gives you the lambda $main $0, And then at the call site, you have an invoke dynamic, which basically retrieve a method handle to the Lambda meter factory and a method handle to the private method, and then throws those to the, or invokes the, throws those to the bootstrap method. So the invoke dynamic takes the bootstrap method handle, the bootstrap method, the Lambda meter factory, and the other parameters, and it creates a call site that is installed, etc. So that takes time, and of course you, in the link phase, well, on first invocation of the invoke dynamic, we will do some just once bootstrapping. The runtime then first retrieves, oh, I already said this. So let's skip to the next slide. So the class generation side is, well, to create the call site itself, we dynamically spin the class for implementing the functional interface, of which the Lambda is supposedly going to implement, and then, that on applying the functional interface, you basically call the static method previously generated by javac. For cases where the Lambda is capturing, the call site will then wrap a method handle to a constructor of the Lambda proxy class. Whereas for non-capturing cases, which basically are those cases that doesn't carry any state, we don't really need to create an instance more than once, so a single instance of the newly generated class is created and returned. Basically, you create a new constant call site and feed that with a bound method handle or method handle dot constant of the instance of the newly generated class. So this, if you look at this through a profiler, you'll see that this, of course, is quite expensive compared to the execution of said Lambda. And you see that most of the time is spent in the spin in the class method of the inner class Lambda meter factory. But there's also other things happening here, the creation of the method handle constants, the constant call set, etc. So by chance, we introduced the constant dynamic feature in Java 11. Brian Goetz and Paul and others have been talking about that extensively in other talks before me. In essence, Condy allows us to translate, delegate the creation of constants to a bootstrap method, very much like we are delegating the creation of a method or method invocation to a bootstrap method when we do an indy. So if what your use of indy does is basically creating and returning an instance of something wrapped in a constant call site, wrapped in a method handle constant, you might as well use Condy. A lot of things fall out of this, of course. One of those is that making all our non-capturing Lambdas bootstrap using Condy instead of indy is pretty straightforward. Doing so removes few of the intermediaries, and it simplifies a little bit of the VM interaction. So if we go back and take Vicenti's implementation for this and run that through our benchmark, we get a pretty good speed up. both a few milliseconds on a single single one run, but also a reduction of about 25% of the overhead relative to indy classes. So yeah, this enhancement has now been baking in the Amber project for some time, namely in the Condy folding branch. So hopefully it should be making its way over to JDK mainline sometime soon. It's it requires a recompilation of your code, of course, but it's still a very good improvement for free. But yeah, it doesn't get rid of that much really. There's a lot of overhead compared to nested classes. obviously, the remaining overhead is the overhead of spinning bytecode in general. And we'll look at ideas for how to improve that even further later. But, well, Lambdas isn't the only use case for indy and dynamic and metaprogramming. And other use cases has been added in Java 9, like namely the invoke string concat. So what indified string concat does is enables the ability for the VM to desugar, or for Javac to desugar, rather than to string builder chains. String concatenation can be desugared to invoke dynamic using a recipe, etc., and deferring to the runtime to take the string concatenation recipe and generating a more optimized form for it. This enables some very substantial optimizations, which Alexei Shipalev has been eagerly demonstrating for the public. But there have also been known startup overheads, which Shipalev also has mentioned. But the question has been, where are those startup overheads? Are they the same as the Lambda initialization? And well, turns out we have to look under this rock as well. So if we take hello concat, a simple program that just does a number of very similar string concatenations, generate a number of them and see how their startup overheads scale up with a number of call sites. We see that, well, even with our optimizations here, the initial startup overhead is quite large still. We still see about 35, 40 milliseconds of overhead for string concat. And it's not only the initial startup, even though there is some, some warm-up is to be expected from something more complicated. The total overhead grows a little bit. It grows a little bit differently, though, compared to Lambdas. And, well, the fact that this is the case is because string concat doesn't generate a class per call site. Instead, it spends its time doing these method handle combinator trees, creating, in the default strategy, it does a lot of drop, fold, insert argument operations, and combines all these to, with trivial method handles to methods that check whether or not the string can be encoded using the Latin 1 or UTF-16 charset, etc. So the time seems to be spent then creating the combinator tree mainly, not doing class generation. So if we optimize bytecode generation, we're not going to optimize string concat. That's a problem. We need other optimizations to get string concat faster. So, but yeah, generally the question can be asked, so with more and different uses of indy, will we see more and different overheads? There are several RFEs and projects which aim to leverage indy in various ways, similar to ISC and others. You can use, for example, string format can be implemented using something very similar to ISC. And Jimmy Lasky has a prototype for this, which sees throughput improvements of up to 40x, which is very nice. But it does have these startup overheads. The trade-off might, of course, favor the throughput dimension, of course. But as we see, when setup is bound to have, these one-off and per call set overheads, we will regress a little bit on startup by making use of such features in more places. But at the same time, we will also, there's a big imperative to optimize the underlying machinery since it will be affecting us in more places. So there's both a challenge and opportunity here. Well, how do we meet these challenges? Well, there are efforts towards better metaprogramming, and some efforts that has been done in the past. Michael Haupt did a humongous work on adding better, improved method handles for Java 9, and something that there might be further improvements to build upon, but also I'll make sure that we leverage these API points when possible. There's a little bit of a problem in my own effort to generate JLI classes at link time, in that they have troubles with anything that is complex and nested chain method handles. Anything that we build up using Lambda form buffers and Lambda form editors, we cannot punch through those chains and trees of method handles, which is one of the reasons we are kind of failing to optimize indified string concat. So more powerful method handled primitives or using class specializer implementations rather than method handled trees when possible might allow us to create things that are easier to generate statically ahead of time, possibly. But, well, maybe on an orthogonal level, we have the promises or musings about Mindy, Cindy, and, well, isolated methods has been mentioned in the past. Basically, well, we want to minimize the runtime overheads of defining and loading arbitrary pieces of code. So can we do that? And what are the tools that should be considered to do that? Well, metaprogramming will help us with the method handles stuff and also with the bytecode generation stuff. Maybe we also need to improve the bytecode generation itself. If we zoom in on profiles for our Lambda generation, we see that, well, not only the ASM tool library that we use, but also the javac invoke code itself is a little bit stringly typed or stringly bound. We spend about 50% of the observable bytecode in doing string transformation from we take class names and then transform them to the JVM equivalents, etc. It might not be the biggest problem, but it's something that irks me. So one thing that maybe was helped by me ranting about this for a couple of years ago was that, well, we should do something better. Said Maurizio, Maximiliador, and Brian Götz. So they wrote a few yeps. No, I'm not claiming they wrote these yeps because my nags, but they surely brought it into consideration that if we had something some better API to represent various primitives for methods and classes and other things that you want to reason about when you're generating bytecode, perhaps that could be used for a lot of things. And of course, Brian Götz came back with something that was even better than I would ever have imagined, with the Condy folding and the code that he was demonstrated here yesterday to basically get rid of lots and lots of intermediary bytecode and just do the thing that you would want in the first place. But on top of all the cool things that Brian demonstrated yesterday, I think there are ways for us to simplify and leverage a symbolic API using class desk and method type or type APIs to build or improve the ASM or do something that is more slightly more efficient. And slightly more efficient might be enough to bridge the narrow gap now between class generation and the static counterpart. Seems I was too fast again. Okay, that was